Okay, kiddos, here are solutions to ideal gas law practice test. So these, you just have to kind of memorize these. I try to not have you or require you to memorize a lot of stuff, but the boiling temperature of water, 100 degrees Celsius and 200 degrees Fahrenheit. I want you to have that memorized, okay? The degrees Kelvin, you can always just convert from the Celsius. And then at what temperature does water freeze? So freezing point of water, that would be 0 degrees Celsius and 32 degrees Fahrenheit. And this is the one with which we're familiar. That's when water freezes or snow forms. Also, it's the melting temperature of ice. Okay, so, all right, this melting and freezing. Okay, both of those happen at 32 degrees Fahrenheit. For us, that's probably the most important one, living here in Mammoth, but know that. Just memorize it. Thanks. And then again, you can convert from Celsius to Kelvin pretty easily. What is absolute zero? So question number 3, absolute zero. This is, you could describe this as a couple things. It's temperature, it's the lowest temperature possible. It's the temperature where all molecules stop moving. So at any temperature, even when water has frozen, the water molecules are still jiggling, just not as much as if it were really hot, So absolute zero would be all molecules stop moving. That is the lowest temperature possible anywhere, deep outer space or in a laboratory. So 0 degrees Kelvin, and if we convert that to Celsius, it's this, and if we convert that to Fahrenheit, it would be this. So know that absolute zero is 0 degrees Kelvin, and that is a temperature at which all molecules stop moving. Okay. Question 4, what we're doing is we're converting. So these formulas, you don't have to memorize these. You'll be given them in a test situation, but you definitely have to know how to use them. So -5 degrees Fahrenheit, we're converting to Celsius. So we would plug in the -5 for the F, pay attention to our order of operations, be careful with the fractions, and we get -20.6 degrees Celsius, or centigrade it's called sometimes. Do this first, and then multiply by 5, and then divide by 9. Okay. Number 5, convert 200 degrees Kelvin to degrees Celsius, so we're plugging in a 200 for K, and we get -73 degrees Celsius, or centigrade. Number 6, we're converting 20 degrees Celsius to Fahrenheit. This one is important because it's room temperature, so you don't have to memorize it like these, but it is a good piece of trivia. So 20 degrees Celsius, we're going to plug in a 20 for the C and end up with F. So plugging in a 20, here you would multiply and then divide and then add. 68 degrees Fahrenheit, room temperature, meaning thermostats are usually set to this. Okay, so 7. List what each variable stands for. So this formula, PV equals nRT, this is the ideal gas law. It's a formula. Hey, those were nice straight lines. And what does it stand for? P is pressure. Pressure is measured in atmospheres. V is volume. Volume would be measured in liters. N, number of moles of gas. So it's not the number of molecules, it's the number of moles of molecules. Remember, moles is a big number. But it is a measure of how much gas there is. R is just a constant, meaning it's a number that you put in the equation all the time. And for us, it's 0.082. And so that never changes, no matter how much pressure there is, or how much volume there is, or how much gas there is, or how hot it is, this is always the same. And then lastly, T stands for temperature, and temperature is measured in Kelvin. All right, so it is important to know these things. Pressure measured in atmosphere, volume is measured in, that's an L, liters, number of moles, so this would be measured in moles, and temperature would be measured in degrees Kelvin. We haven't used this for calculations. We might, but for now, just know what they stand for and what units we actually use. Okay. Number 8. So these are describing situations, and some of these we've seen, and some of these you sort of experimented with that simulation on the computer. But let's see. You heat up a metal container with an open lid. What happens to the air inside? So you're heating up a container with an open lid, so it'd be like this. What happens to the air inside? So originally you'd have these gas molecules like that, okay? And if you heat it up, what happens is they're going to start moving back and forth faster, and they would actually spread out because some of them would leave the container. So what I say is they move faster, they expand, air leaves the container. So air molecules would actually leave if you heat it up. Then, and what happens if you close the lid and let it cool down? So now we're closing the lid, we have fewer air molecules inside. So if we have fewer air molecules inside, it means N is now less, okay? And so when the temperature decreases, all of a sudden we have less over here, so we need less over here, and that takes place by the pressure decreasing. So pressure decreases, and the outside air pressure is 14.7 pounds per square inch, or 1 atmosphere, okay? And eventually the can would collapse. So what happens if you close the lid and let it cool down? No air is allowed to enter or leave because it's closed. As the temperature decreases, so does the pressure. So we have fewer air molecules inside. Temperature decreases, pressure decreases, and the air pressure outside the container eventually collapses the container. As I tried to demonstrate and failed miserably, but we saw a couple videos that were kind of cool, and people actually succeeded in that demonstration. All right, number 9. When you pump air into a bike tire. Okay, so pumping air into a bike tire, and maybe I should show you this. Which variable are you controlling and what variable is affected? So the difference here is this is what you do and this is what happens. Okay? The variable you're controlling is the thing you're actively doing, and then this is a result of that. So when you're pumping air into a bike tire, you are increasing the number of molecules, and the variable that is affected in the bike tire is going to be the pressure. So because volume remains the same, the pressure increases. Bike tires don't really expand when you pump them up. Okay, once there's a little air in it, the tire actually keeps it in the same location. A bicycle tube would be more like a balloon. So maybe I can demonstrate that to you, but there is a difference. But the pressure increases. Okay. 10. When you heat up a closed metal container, what variables stay the same? So it's a closed metal container, so the volume would stay the same. It doesn't change shape. Okay, it's not like a balloon where it puffs up. What variable are you controlling? Well, you're heating it up. You're changing the temperature. And then what variable is affected? That would be the pressure. So this would be like we have a closed container, a certain number of molecules inside. Heating it up doesn't change how many molecules there are. What it does is it changes how fast they're going. So they're going kind of slow, and you heat it up, and they're going bung, 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 like that, increasing the pressure. So the pressure would be pushing out on the sides of the container. Okay, lastly, number 11, when you take a full balloon and place it in a freezer overnight. Full balloon, and place it in a freezer overnight. What variable stays the same? What variable are you controlling? What variable is affected? So, full balloon, here's the balloon. We have some air molecules inside, okay, and they're pushing out, which makes the balloon puffy like this. And we're going to put it inside a freezer. In that simulation, there were these blocks of ice to indicate cold. And what would happen is the air molecules would start moving slower. Okay, so let's take a look at our ideal gas law. Uh-oh, the balloon is not moving. Let's take a look at this. What we're doing is the number of molecules stay the same. R always stays the same, but we're decreasing the temperature. So if this decreases, something over here has to decrease. Okay. But the air pressure inside a freezer is the same, so the volume will decrease. So there's our balloon, and here's our cold. So the molecules are moving back and forth more slowly, and the balloon would shrink to a smaller balloon. Okay? So the volume from this decreased to this. Number of molecules and the air pressure, again, the air pressure outside is the same as inside the freezer. All right, they stay the same. We control the temperature, and what is affected is the volume of the balloon. Aha! Okay, good work. There's practice test number 2 with similar questions. See if you can do that and get them all right.